So our next speaker, Dennis Hartmann from University of Washington, Pacific Ocean SST and the winter of 2014.
Thank you, Mike. It's a great honor to be here speaking in front of this group on this august occasion. I was looking at the photos on the Shukla page, and it reminded me of when Shukla and I met. By the way, I have documents to prove that today is my birthday, but I'm not yet 70, but it's wonderful to share it with you all. Anyway, Shukla and I were graduate students at the same time, and he was a student of Charney, and Charney sent Shukla down to GFDL to learn about climate models or something like that. And Joe Smagorinsky was a great friend and admirer of Charney, so he squired Shukla around and introduced him to all the graduate students, and it was, even then he had an aura and a gravitas about him. It was very clear to us that he knew more than most of us, and he was destined for great things, which turned out to be the case. So, very happy to be here today. And later on, I was one of probably many of you who served on the COLA SAG. Always a very interesting group. So I really appreciated that opportunity to meet some people. And it was a very easy job because all we had to do was to confirm to the rest of the world that they were doing great stuff there. So it was a very easy and enjoyable job. Thank you very much. All right, on to my topic. Of course, here's a graphic from the New York Times in January saying that 2014 was the warmest year on record, but unfortunately, perhaps for the Earth, it was a relatively cold year for most of the population of the United States, and that's the topic of my talk today, more or less, is talking about how that might have happened. And quite a few opinions about it. Some people saying that it's the Arctic, and Tim Palmer, who's here, is already on record saying it's about part of global warming, or could be, at least. An article here that he wrote for Science magazine, I think. And we do live in interesting times. The last 15 years or so, the northern hemisphere and the southern hemisphere have diverged greatly. The global mean has sort of leveled off, but the continents in the northern hemisphere are still experiencing extremes that we've never seen before. So we're living in a very, very interesting time, and a very interesting time for predictability of the global climate. If you look at the trends since 1979, you can see part of the reason for that. The northern hemisphere continents are warming up, and the southern hemisphere ocean is actually cooling down, and there is this La Nina trend that has been much discussed. And I just wanted to that's a Robinson projection. I wanted to show it in an equal area projection so that it kind of indicates how small the Arctic is compared to the tropics, where it's been warming in the western Pacific and cooling in the east over that period. And that's something that we've seen a bit in the last few years. So if we go to talk about the Pacific Decadal Oscillation, which Mike was involved in defining, was a while ago. So they used the sea surface temperatures north of 20 north in the Pacific in that little box there. And if you do that with the data now, you find that the PDO is still the dominant mode, but there's something second mode, which is also significant, which I think Clara Desser called the North Pacific mode, so I'm using that terminology, which is the second most important one. And that has a, what we call in the West, a blob of warm sea surface temperature in the North Pacific. And it does trail off in sort of a C-shaped structure off to the tropics, and structurally it looks very much like the Atlantic multi-decadal oscillation. Actually, in terms of its genesis, it involves a dipole pattern in the height field. PDO, I think, is well, let's talk about that. So if we extend the domain to 30 south, we have better data now. Then we get ENSO is dominating. Once you include the tropics, ENSO really dominates. But there are two other modes that stand out above the noise according to the Jerry North criterion, who's also here today. Eigenvalue spectrum on the right. There are two decadal modes. So ENSO is the mode on the top. The EOF2 is the persistence of ENSO, I would say. And then the third mode there is the North Pacific mode. And if you look at the time histories of those since 1979, you can see, for example, the 1983 El Nino there, and then there was a very strong La Nina in about 89, and then the 1998 El Nino. And what I want to point out is that at the present time, if you look at the right-hand side of those plots there, the PC3, or the North Pacific mode, has been like 2 standard deviations above normal for the last couple of years and remains so, whereas the other 2 modes of variability are near their neutral points. So you can then argue that what we're experiencing now may be related to the fact that this third mode is 2 standard deviations or more above normal. If we look at the temporal relationships between those 3 things, the blue line on the top there is the autocorrelation function for ENSO, which has a sort of a periodic looking structure. It has a time scale between 2 or 6 years. If you compute the power spectrum, it has a peak in that range. The second 2 modes have almost identical autocorrelation functions, and they show very strong autocorrelation at about 12 months. And we think this is related to the in the wintertime, a heat anomaly is buried in the North Pacific, and then it emerges the next winter, covered over in the summer, and that gives us a persistence at 12 months and gives the much longer time scale associated with these 2 modes. If you then look at the lagged relationships, the lower plot there, you can see that the third mode, which I'm calling for the sake of convenience, the PDO, sort of follows after it, and we think that's because the extratropics remember ENSO longer than the tropics do. And the North Pacific mode actually leads ENSO. The correlations there are not huge, but they are statistically significant. They're around 0.3 or 0.4. And the North Pacific mode related to ENSO has been called the seasonal footprinting mechanism, so this has been recognized before this particular structure tends to precede ENSO. So we think of the first one as ENSO, the second one is a delayed response to ENSO, and the third one, the North Pacific mode, is sort of a precursor mode that tends to occur before ENSO. And these all have a very strong expression in the wintertime 500 millibar height field. So what's shown on the right are the correlations of the 500 millibar height field, actually the regressions of the 500 millibar height field with the principal components of those 3 sea surface temperature patterns shown on the left. And the top one's sort of the classic El Nino signature with cool and wet in the Gulf states and rain in California that Jim already mentioned. And the third one has this dipole pattern in the height field over the Pacific, with the high sort of reaching down into California, and a low pressure system over the eastern US. And that would be the pattern that we've experienced, say, in the winter of 2013-14. The top graph there, I think, is the observed anomaly for November to March, the average over that period for our previous winter, with the ridge over the west coast and that very deep trough over North America, which gave us a very cold winter in the eastern U.S., particularly Chicago had the second coldest winter in record. And the middle shows the regression of the third mode, the red line in the left panel, with the geopotential height over the period of the NCEP DOE reanalysis, 48 to 2014. And the bottom panel shows the regression of the 500 millibar height field onto global mode 2 for the period from 1979 to the present. So this North Pacific mode has become more dominant in the recent era for reasons that I don't understand. And if you regress the near surface temperature onto that mode, you do see the cold in the east, warm in the west pattern near the surface. And you can even see a relationship to the summertime temperature. You may remember that the summer, was it last summer, was relatively cool in the east, and that's what this regression pattern tends to tell you. The regressions are much less significant in the summer season, but still they are there, predicting a cool summer. So that's predictability. This is the closest I've gotten to predictability in my research, so I thought it was appropriate. So then I guess so that's just a correlation. So we have to demonstrate that those sea surface temperatures are actually producing those height anomalies. And it's fortunate that NOAA produced a large set of simulations related to trying to understand the California drought that I could use for my purposes, which had 3 different models and relatively large ensembles. I just downloaded the ensemble mean and regressed that onto my EOF3 of the sea surface temperature. So on the left are shown in the lower panel there, the sea surface temperature anomaly associated with the North Pacific mode. The upper panel on the left is the regression that I showed you previously, and then on the right are the regressions of the individual model simulations for the period from 1979 to 2012 onto that sea surface temperature pattern. So you can see that those 3 models are each producing at least the ridge along the west coast, the trough in Pacific. The downstream trough over North America is harder to get in these models. I'm not quite sure exactly why. It's a little bit on the end of the wave train from the Pacific. It's definitely there, but it's weaker than in the observations. So then we know that the sea surface temperatures are in fact driving these anomalies. And based upon previous research, we would presume that the driving is coming from the tropics, and we've in fact verified that with simulations. I can show you later, but I probably don't have time. You can show that if you introduce the sea surface temperature anomalies in the extratropics, it does very little. But if you introduce the sea surface temperature anomaly in the western equatorial Pacific, you do get the patterns very clearly. Thank you, Mike. I see you. Right. So this is related to the drought, and I think this is pretty close to the end. So this is extending that into the 2015 winter. So this year it was snow in Boston, and the sea surface temperature anomaly has evolved, as you can see on the left. In previous winter of 13-14, we had what we call the blob, very high, like 3 standard deviations of sea surface temperature, and that has moved eastward, hugged along the coast, caused a lot of problems with the biology of sea lions and things like that. And the atmospheric pattern has also shifted a little bit to the east, so suggesting that this winter has also been associated with those sea surface temperature anomalies. The tropical sea surface temperature anomalies have evolved from that warm anomaly in the far west Pacific to something that looks more like the beginning of El Nino. But you can see that the sea surface temperature increased actually more in the west and central Pacific than it did in the far east. So it's still more like what the Japanese call El Nino Modoki, or pseudo El Nino, than a classic one. And here are my conclusions, which I think are perfectly clear, and thank you for your attention. Right.
One of the key things I think for me is why we got such strong Rossby wave generation in that winter was how far north the convection was in the winter hemisphere.
Mm-hmm.
Really unusually far north. Our model, the seasonal forecast model, is getting enhanced convection in that region, but of course they were tending to keep it in the traditional realm of on the equator or south of the equator. And here we had kind of quite disturbed weather across the Philippines, as you may remember, and similarly again this winter, actually, with the warmth of the water being actually rather full. So it seems to me that when we want to try and understand these things, we also need to look at the details of what's happening with the convection and these waves that Brian was talking about, in a sense, where they're sitting in relation to the being able to interact with the Pacific jet. So I think we had actually a really quite subtle but very interesting setup last winter. And again, I think this winter too, the convection's been quite north of the equator. So it's just a little additional bit of predictability that I think we can extract if we think about where the heating is and not just where the SSTs are. I should say I think the warmth of the West Pacific, tropical West Pacific, is deeply intriguing. Yes. Because it's stifled one El Nino and will it stifle another El Nino this year? And what does it mean for Californian drought and so on and so forth?
You could plausibly think that this change is somehow related to global warming, but unfortunately the climate models can't give us any very consistent guidance on that. What should happen to El Nino?
Yes, or is it just the ocean's circulation on these slow modes, which we understand so little about?
It's really hard to know.
Dennis, I agree with you on the origins and the tropics, but one of the things you might want to look at is the precipitation anomalies. And during the winter of 2013-14, that was the time, you may recall, when there were a tremendous number of strong westerly wind bursts in the tropical Western Pacific. And for that winter, just north of Cape York in Australia, right on the equator, the anomalies for the whole winter, 90 days, were 9 millimeters per day rainfall anomalies. Incredible heating of the atmosphere as a potential source of Rossby waves into the extratropics. So it would be a really nice extra diagnostic for you.
Right, and kind of more than you would expect based upon the sea surface temperature anomalies alone, maybe. Yeah.
A very quick question. Back in the early 70s, Mike Wallace and I had a symposium at the Science Center to explain the great drought that occurred in the early 70s. And I was just wondering, by the way, nobody turned up because the drought broke the week before the symposium. But I was wondering about the cause of that earlier drought. Was there a similar blob at that stage back in the early 70s? Which would be interesting because that's a time before, of course, all the warming occurred. So it would be an isolation of the impact.
Yeah, I think both La Nina and this mode kind of produce drought in California. And I have not looked in detail at the 70s to see if there was a similar sort of pattern or not.
I think that was 76, 77, if I recall, right? It was an extreme year.
Yeah, we argued about that.
Yeah.
And I think that was a very strong La Nina period, but yeah.